Let's get started with a simple mathematical problem. Here we have unknown variables a, b, c, and d. Using the numbers around them, we can find these variables. If you add the numbers horizontally, then you're going to have the numbers on the right-hand side. If you add the numbers vertically, you're going to have the numbers at the bottom. For example, if you add a and b, then you're going to have 7. If you add a and c, then you're going to have 8. If you add diagonally, which is a plus d, that is 5. Now, can you find a, b, c, and d? Well, why do we have to do this? If you understand this simple mathematical problem, you will be able to understand how the computed tomography works. Hey guys, I'm Professor Peter. First of all, let's finalize the mathematical problem that I gave you. If you write down all the constraints as equations, then you're going to have 5 equations, and one of them is redundant, so you can use only 4 of them to solve this mathematical problem. If you add these 2 equations, then you're going to have this, and we know that a plus d equals 5, so if you plug 5 for a plus d, then you can determine c, which is 5. You can plug 5 for c in other places, then you're going to get the answer. The final answer is this. In computed tomography, which is also called CT, you have to solve this type of mathematical problem. Before we talk about the details of mathematical technique in computed tomography, let's talk about how the CT equipment collects the data. CT equipments are basically using X-rays. As you see here, let's assume that we want to get the cross-section image of the human body. We have the X-ray detectors on the right-hand side. We have the X-ray emitter on the left-hand side. Then we shoot the X-ray on the spot where we want the cross-section image. It is similar like cutting a tofu using a sharp knife. So the X-ray image is not two-dimensional. It is just one-dimensional image. If you look at the details of this one-dimensional image of X-ray, depending on the location, you will see different X-ray intensities. Let's call it X-ray projection. When the X-ray penetrates the body, the intensity of the X-ray will be reduced. The X-ray intensity will be reduced much if it penetrates bones, but if the X-ray penetrates fat or muscles, then it will not be reduced as much. Now let's connect the data collection in CT equipment and the mathematical problem that I gave you. Okay, let's assume that these 4 numbers are representing the cross-section images of the body, and each number represents the amount of reduction in X-ray intensity. For example, number 5 represents bones, number 2 represents fat. Actually, I talked about these numbers in the previous clip. These numbers are called attenuation coefficient. Now, let's shoot X-ray with the intensity 10. When it goes through the top row, the X-ray intensity 10 will be reduced by 3 and 4. So remaining is just 3. 10 minus 3 minus 4. If you consider the vertical direction, then you're going to have 2 here because 10 minus 3 minus 5 equals 2. Along the diagonal direction, we have a 5. As you see here, X-ray projection suppresses the detailed information. As you can see in the top row, the remaining X-ray intensity 3 doesn't tell you the details like 3 here and 4 here. Now, by comparing the original intensity of the X-ray and the remaining intensity, you can find how much X-ray intensity was reduced. For example, in the first row, the X-ray intensity was reduced by 7. In the left column, the X-ray intensity was reduced by 8. If you put these numbers, then you have exactly the same problem that we had. By assigning the brightness for these numbers, you can have the CT image. As you might notice, I simplified the real situation. Real situation is more complicated. in order to have a high quality image of cross-section of a human body, the resolution of the image should be very, very high. In order to find the brightness of many pixels, you need more information, which means you need a lot of projections. Actually, you have to take X-ray projection in various ways. That's why the X-ray equipment looks like a circular shape. Inside the equipment, X-ray emitter and the detector are rotating around so that it can take a lot of X-ray projections. Now, does the CT equipment really solve this mathematical problem in this way? Of course not. First of all, the number of pixels of the required image is too high. In addition, to find the brightness of many pixels, you need more and more equations. For example, if you want a 500 by 500 image, which is relatively small, you need to determine the brightness of 250,000 pixels. To do that, you need at least 250,000 equations. Solving that equations is not efficient. Here, you can use a very important mathematical tool, which is called slice theorem. In engineering, we have very famous tool which is called the Fourier Transform. Slice theorem is based on Fourier Transform. Using the Fourier Transform, you can change signals or general information into different form. We actually use the Fourier Transform many times. One of the examples is equalizers. The sound equalizer converts the sound information to frequency information. Using equalizer, you can boost the high frequency information like this, or you can boost the low frequency information like this. So as you see here, using Fourier Transform, you can play with frequencies in sound. In addition to sound, you can apply the Fourier Transform to general functions or even images. Okay, here we have a cross-section image of a body, and its Fourier Transform looks like this. Fourier Transform of an image doesn't look like a meaningful image to us, but it's okay. It's just a mathematical transform. Well, because we are looking for 2D cross-section image, let's put question mark here. The thing that we have is X-ray projections. As I said earlier, the X-ray projection actually suppresses the information, and it is one-dimensional information. Here, you can apply the Fourier Transform on this X-ray projection. Surprisingly, this Fourier Transform of one-dimensional information is exactly same as one slice in the 2D Fourier Transform result. So now we can have a kind of a multi-step process. First, we have many projection data, and then we convert it using Fourier Transform, and we're going to combine it to have two-dimensional image. This two-dimensional image is not real image. It is a Fourier transformed image. So in order to get the cross-section image, we have to apply the inverse of Fourier Transform on this. Then we have the result. For those who are interested in the mathematical proof for this, I put the link down there. In CT imaging, we need many projection data. That means we have to take X-ray many times. Because we have to minimize the radiation exposure, the X-ray intensity in CT is also limited. As a result, a long time ago, the CT image quality was not that good. But these days, we have better and better mathematical algorithms as well as very efficient computers. So we can take a CT image relatively easy and safe. That's all for today. Thank you very much for watching. See you next time. Bye.